This would be our last example, identification of subgroups of any identified group. We have here the group containing the elements 1, 2, 3, 4, 5, and 6. And yes, we have verified this in one of our videos that this is a group under multiplication modulo 7. So we are to identify now the possible subgroups of this given group. And take note that we have here 6 elements. We understand that subgroups as defined are also subsets of the given group. And if we have 6 elements, we know that in our basic mathematics, the number of subsets that we can draw is 2 to the n or 2 to the power of 6. If I'm correct, that's actually 64. That's 2, 4, 8, 16, 32, and then 64. Yes, there are 64 possible subsets. And if we're talking about subgroups, there are 64 possible subgroups. And yet here, we are to determine them in this specific video. Hopefully, we will not be trying all 64 possibilities. However, we are going to try here the help of the Lagrange theorem. Okay? The Lagrange theorem will trim down our process, because if we're going to take the cardinality of our group, we know that it's 6. It contains 1, 2, 3, 4, 5, 6. Any subgroup H, according to this theorem, will have a order or cardinality which are actually positive divisors of 6. The positive divisor of 6 is 1, 2, 3, and then 6. What does this mean? We are assured, according to the Lagrange theorem, that our subgroups are having order, cardinality, or size of 1, meaning we have a subgroup of 1 element, we have a subgroup of 2 elements, we have a subgroup of 3 elements, and finally we have a subgroup of 6 elements. What is the point of this being discussed? We may trim down our process because there's no need for us to try 5 and 4, meaning any subset of 4 size or 4 cardinality or order of 4, or even 5. That would mean the 64 possibilities is not just 64, it will be trimmed down to even smaller attempts. Okay, that is why we have here the Lagrange theorem. It would even be trimmed down later on by some of the axioms of group, because subgroup is of course a group in its nature. It should contain the idea of the axioms of being a group. Let's now start with the identification of the first subgroup. Always remember that the group itself containing 1, 2, 3, 4, 5, and 6 is a subgroup in itself, because we know that a set is a subset of itself, and since the group or this given set here is already a group in its nature, it follows all the axioms, so the group is also a subgroup of itself, and it even clarifies that it's one of those possibilities for the size of a subgroup according to Lagrange theorem. It's actually the subgroup of size 6. Okay, that's the first one. The second one is pertaining to this one here. We are going to talk about the subgroup of order 1. Yes, that's the second. The subgroup of order 1 is actually the subgroup containing the identity element E. If you can remember, this given set was already proven to be a group in one of the videos. And in that specific video, we also discussed its identity. And since we're just talking about the same set and we have the uniqueness of identity element, the same identity element discussed in that video is the identity element that should be placed in this set for the subgroup of order 1. Or, if you're not convinced with that video, let's look into our KD table here. We can identify the identity element in our KD table looking into the couple of rows or columns that do not change its value with the corresponding elements, stating that if we have 1, 2, 3, 4, 5, and 6, when we operate it to 1, you will still get the same results. Similarly, if you have 1, 2, 3, 4, 5, and 6, operating it to 1, we will have the same result. This would mean that our identity element is actually equal to 1. We have here 1 star 1 is 1, 1 star 2 is 2, 2 star 1 rather, 3 star 1 is 3, 4 star 1 is 4, 5 star 1 is 5, 6 star 1 is 6. All of this, when operated by 1, will not change their value. Similarly, if we use 1 star 1 is 1, 1 star 2 is 2, 1 star 3 is 3, 1 star 4 is 4, 1 star 5 is 5, 1 star 6 is also 6. When we operate 1 to any of the elements, those elements retain their value. This is a further proof that really our identity element is 1. Again, you may also try to review the video in the verification of this set G as a group. So basically, our subgroup of order 1 is a set containing 1. So we're already okay with that. The next here is looking into the non-trivial or the proper subgroups, because the set itself is improper subgroup. This is a trivial subgroup. So for those subgroups with less than the total number of elements or cardinality are called to be non-trivial, except for one which is called trivial. So for our set here, let's talk about order of 2, because that's the first thing here, order of 2. So if we have order of 2, meaning we have pairs of elements. Take note, we have 6 elements here, and if we're going to look at pairs of elements, we might have a lot to try. That's why let's introduce the axioms now for groups that's also applicable for subgroup. The first here is the existence of identity element. By the way, we will no longer use here or try the identification or verification use of associativity, because since this is already a group in its nature, that would mean any subsets will also take its associativity. That's why we automatically proceed with existence of identity element. So that would mean here, the point being here is our subgroup or candidates for subgroup of order 2 must contain or the identity element in its pair. Okay? Because that's the axiom for a group, and subgroup is a group. In short, our trial here or candidates would be 1 to be paired with 2, 1, 3, 1, 4, 1, 5, and 1, 6. Take note that there are 6 different elements, and if we are going to talk about pairs of elements out from 6, there are a lot, but we only need to try 5. We don't need to try 1 and 1 because it's just the same as that, no duplication. And of course, we will no longer try 2 and 3 or 5 and 6 or 4 and 2. These are no longer possible because again, our subset to try must be a group in itself. So identity element of 1 must already be in that pair. So since 1 are not here, they are no longer possible. That means, again, instead of a lot to try, we only have 5 to try. So what would be the next? Again, identity elements are already here. So we are going to proceed with the next, the existence of inverse elements. Sorry. When we talk about inverse elements, we know that there are different or there might be unique inverses for any element. So for this first pair, we need to examine whether the inverse of 1 is here and the inverse of 2 is also here, so that this second axiom is satisfied. In order for us to do that, let's go back to our KD table. And on our KD table, we can actually check the possible inverses, or the inverse, not necessarily possible, the inverses themselves, because we can actually look at the grids. Take note that the inverses, when operated, will result to our identity, and our identity is 1. So this is 1. There is 1 here, 1, 1, 1, and 1. The point here is that for those grids with result of 1, look at the elements being operated and you would see the inverses of the other. Let's start with 1 star 1 resulting to that. This supports that the inverse of 1 is 1. For our 2, it's here. That's actually 2 star 4. Okay, so the inverse of 2 is 4. For our 3, it's here. So the inverse of 3 is 5. 3 star 5 is 1. So the inverse of 3 is 5. Now for 4, it's here. 4 star 2. So the inverse of 4 is 2. For our 5, it's here. The inverse of 5 is 3. Okay? And finally, for our 6, it's here. That's actually 6 star 6. So the inverse of 6 is itself. So the point of this is that the corresponding inverses must also be placed in the same set in order for us to consider that any of these candidates with order 2 are subgroup of, or is a subgroup of the given group. Let's talk about the first one. The inverse of 1 is 1, but the inverse of 2 is 4. Therefore, we drop that. You might say, what if I will add here 4? So that's no longer order of 2 because you have 3 elements. So we might have it on a separate option later on because we are guaranteed to have order of 3. This time, we drop that. Next, we have 1 and 3. So the inverse of 1 is 1. The inverse of 3 is 5. It's not there. Drop that. Next, for 4, 1, inverse of 1 is 1. The inverse of 4 is actually 2. Drop that. Then for 1 and 5, the inverse of 1 is 1, but the inverse of 5 is 3. Drop that. How about 1 and 6? The inverse of 1 is 1. The inverse of 6 is 6. So this is okay to be validated by our last step. We cannot say that it is already a subgroup because we need to identify the possibility of the closure property. And this is the last to use in checking whether it's really a subgroup. But it's really a candidate because it contains the identity element and the inverses of the other. For closure property, this tells us that if we're going to operate 1 to 1, 6 to 6, and then 1 to 6, and 6 to 1, would the result be either be 1 and 6? If the result would be other than 1 and 6, then we drop that as well because closure property is not satisfied. So in our k-list table, you have here 1 star 1 is actually 1. Okay? So 1 star 1 is 1. 6 star 6 is actually 1. How about 1 star 6? 1 star 6 is 6. And then you have 6 star 1 is also 6. We can see that the results are either 1 and 6. They're all elements to that. So aside from it containing the identity element and the inverses of the other, it's closed under the same operation using our k-list table. So this is our subgroup of order 2. So we need to move to the next one because we still need to identify subgroup of order 3. Now, subgroup of order 3, as mentioned, similar to this form, it would be the combination of 3 different elements. But we might have a lot of combination to try. So what would be our strategy here? Okay, my strategy is, of course, always include the identity element. So our groups of 3 will have here, or order, subsets of order 3 must contain 1 as well, because identity element must also be contained in that. And then secondly, the existence of inverse elements should also be there. Going to our third group here, where we have order of 2, this was dropped, right? This was dropped, this is also dropped, and this is also dropped because they lack another element that would satisfy the existence of inverse elements. So what if we try that 1, 2, and then we know later on that the third one would be the identity element of 2. Similarly here, 1 and 3, and then 1 and 4, and then we have here the last one, 1 and 5. Okay, so because 1 and 6, if we're going to try 1 and 6, we will be stopped here because it already satisfied the subgroup. So we have 1, 5, 1, 3, 1, 4. We'll be looking for the third element to have our order of 3. We are using this other than 2, 3, 5 because then again, there is no identity here. So we actually anchor it to our, this is no longer, this is actually IV. So we anchor this one to our step, our group number 3. So going back here, the identity element is already here. The inverse of 1 is also 1. The inverse of 2 now is actually 4. So what if we add here 4? And then we check again inverses. The inverse of 4, okay, is actually 2. It's already there. Focusing on the first 2, this subset of order 3 satisfy the existence of identity element and at the same time the existence of inverses. So we'll proceed to our third one. Let me erase this 1 and 5 here, okay? Because we need to identify this verification, or we need to satisfy the closure property. If we have 1 star 2, 1 star 4, 1 star 1, you have 2, sorry, you also have here 2 star 2, 2 star 4, and 2 star 1, and you have here the last group 4 star 1, 4 star 2, and 4 star 3. We will be trying all of this and verify whether the results would still be included here for closure property. Take note for 1, since 1 is the identity element, you can also verify it here. It will not change the values. This is still 2, 4, and 1. This is 2, this is 4 as well. Because when we operate any element by itself, by 1 rather, it's itself. Now let's have 2 star 2. 2 star 2 is actually 4. 2 star 2 is 4. So it is 4. How about 2 star 4? 2 star 4 is 1. So all of this also satisfied. How about 4 star 2? 4 star 2 is actually 1. And then 4 star, sorry, this should not be 3, right? 4 star 4. 4 star 4 is this one here. 4 star 4 is this 2. So we can see here that it's already close. Aside from having the identity and all the inverses already there, all of the results when they are actually implemented or operated using the given operation would still have closure property. So this is our what they call this one, subgroup of order 3. Now let's not stop here because there may be other possibilities as well. We have erased actually 1 and 5 earlier, so we will return to that. As to 1 and 3, what made this actually drop earlier in order to it's because when you have the inverse of 1 is 1, but the inverse of 3 is actually 5, right? So we need to add here 5, and let's try to close that. So we have the identity element is here. Sorry, the identity element is here. Okay, the inverse of 3 is actually here, 5. Okay, the inverse of 5 is here. So let's now check the closure property for this. So 1 star 3 is still 3, 1 star 1 is still 1, and then 1 star 5 is 5 because 1 is the identity. So probably it could also be another, because the Lagrange theorem is only telling us that there are possibilities for the existence of specific subgroups of order n, or order factor of our n, which is the cardinality of our group. But it did not tell us that there's only one subgroup of order 3, only one subgroup of order 2. Let's try all. So what if I have 3 star 3, because 3 star 1 is still 3, right? But 3 star 3, when you have it here in our kitty table, 3 star 3 is actually this one, 2. So 3 star 3 is 2. Since this is 2 and 2 is not an element of the given or our trial, we drop that automatically, because what you need to do is of course add 2 to make it good, and then go back again to inverses, etc., etc. But since we are on order 3, we drop that. This is also similar to the last one I erased earlier, 1, 5. Since the inverse of 5 is 3, so 3 will appear here, and we'll have the same elements as that, so we actually drop this as well. So we only have one remaining to try. So this is 1, 4, and the inverse of 4 is actually 2. But take note, this is just the same as this set here, or subset, because we talk about sets, it disregards the arrangement as long as we have the same elements. So this is also considered as a subgroup, but we only write it once depending on which you would prefer. So this is now the order of 3. We have 1, 2, and 4. Again, we will no longer try order of 4 or order of 5. because according to the Lagrange theorem, we only have orders 1, 2, 3, 6 for possible subgroups of the given group. So now we all have this. Let's now try to summarize our step. Okay? For the subgroups of the set given as 1, 2, 3, 4, 5, and 6, this is our set G. The first subgroup is, of course, the set itself. 1, 2, 3, 4, 5, and 6. That's the subgroup of order 6. Next is subgroup of order 1. Then for subgroup of order 2, it's actually 1 and 6. And then a subgroup of order 3 is 1, 4, 2 or 1, 2, 4 when you would like to have it arranged in ascending order. So we have 4 subgroups for this given group here. Now we have a way to make this subgroups also placed in order. We call it lattice or subgroup diagram. We'll have it later, because after we identify the subgroups, it's also nice for us to really place them in a specific diagram or organize them so that we will be guided as to how would the subgroups will look like when they are interrelated to one another, and of course to our given group. We will have that later. Thank you very much for watching.